going to head back to the stock market now to discuss betting strategies on stock prices. That is, what is your best strategy for buying and selling a stock? We're going to model our stock price as a submartingale with respect to some filtered probability space. You, the investor, have some initial fortune that we'll call W0, and then at each time step, you're allowed to buy a certain amount AN of the stock after its price at time n minus 1 is set. As we've discussed, to have a remotely realistic model, that sequence AN of purchases must be a predictable process. You have to decide how much to purchase at the next time step based on the information that you had up until and including only the n minus first time step. Now, your fortune at time n is therefore equal to your initial fortune, W0, plus this stochastic integral, in of a and x, which in this discrete setting, as we've seen, is just W0 plus the sum, j going from 1 up to n, of aj times delta xj. Now, the question is, given this setup, what is your best strategy? You'd like to maximize the profit that you make and minimize the loss. So what should you do? Well, the time-honored traditional betting strategy is to buy low and sell high. To be more precise, as we'll get into later in this lecture, you set some minimum price A and some maximum price B. And as soon as the stock falls below price A, you buy. And then you hold on to your stocks until the price eventually, hopefully, rises above price B, and then you sell. If you do that, then you're guaranteed to make a profit of B minus A during that whole trade cycle, provided that the price does ever reach B. Now, it might seem like a difficult question to answer whether this is the best betting strategy or if there's something else perhaps more complicated and more sophisticated that could do better in the long run. But actually, it's not a deep or sophisticated question at all. The answer is no, this is not the best betting strategy. And the best betting strategy is the simplest of all, although it seems too bold to work. To be clear, we have to add an extra constraint, which again is quite realistic from a real stock market perspective, that there is a daily limit to the amount you're allowed to purchase. So let's just normalize things and make that limit 1. You aren't allowed to buy more than one amount of stock during a given trading period from n-1 up to n. That is to say, our function an must take values in the interval from 0 up to 1. Under that constraint, it turns out that the absolute optimal betting strategy is the following dumb-sounding strategy, all in, which is just to buy the maximum possible amount at each time step. To see why, we need to note two things. First of all, how do we test whether a strategy is good or not? The answer is to check the expected value of Wn. We want the expected value of Wn under our particular betting strategy, Aj, to be the maximum it could be. And the second point is, to see why the all-in strategy is best, we need to check to see what our expected fortune Wn will be in the case of employing the all-in strategy, which means setting all of these to V1. Of course, that's quite easy then. This is just a telescoping series. x1 minus x0 plus x2 minus x1 plus etc. up to xn minus 1, all the intervening terms cancel, and we just get that Wn is xn minus x0, the price of the stock at the last trading time minus the price at the initial time. So that's what we get with the all-in strategy, and the theorem is that no matter what predictable strategy you use, if xn is actually a submartingale, then the expected value of the amount of your fortune that you've accrued up to time n beyond your initial amount is never more than the expected value of xn minus x0. That is, no matter what betting strategy you employ here, you can never do better than you would do with the all-in strategy. To prove this, let's just take the complementary betting amount to whatever you do bet. Cn is 1 minus an, the amount that you have left over that you don't buy at each time step. Well, because an is in the interval from 0 up to 1, Cn is still greater than or equal to 0, and of course it is still predictable. since an is. Now, since our stock price xn is a submartingale, as we proved in the previous lectures, the stochastic integral of c with respect to x is also a submartingale. That's because Cn is predictable and non-negative. In particular, it follows that the expected value of that stochastic integral is greater than or equal to 0, the value at the beginning, since we're talking about the increment to your fortune here. So that's the expected value of the sum, j going from 1 up to n, cj delta xj. That expected value is non-negative. But if we now just use the telescoping property to expand xn minus x0 as we did before as the sum of all of the increments of x, and now we note that cn plus an is constantly equal to 1, we can put in that 1 here in the form of aj plus cj, and write this in the form the sum, j going from 1 up to n, of cj delta xj, plus the sum, j going from 1 up to n, of aj delta xj. But that means taking expectations that the expected value of the total increment in the stock price is the expected value of the stochastic integral of c with respect to x plus the expected value of the stochastic integral of a with respect to x. And as we noted above, that's non-negative. So therefore this is greater than or equal to the expected value of the stochastic integral of a but that's exactly what we wanted to show. So if you're betting on a submartingale, you should go all in every turn. Now maybe you feel a little unsettled with that idea. Maybe you don't think that submartingale is a good model for the stock price, or maybe you just don't want to lose all your money at once and want to have a better guarantee of gains even if they're not maximized. So let's do a little bit of analysis of the buy low, sell high strategy, which is something that many investors would feel is safer. We fix two thresholds, A and B, with A less than B. And again, the strategy is we wait to buy anything until the price drops below A. And at that time, we buy the maximum amount allowed. Then we hold on to those stocks until the price eventually rises above B, hoping that that does eventually happen. And then we sell all of the stock at that time. And then we repeat. We wait again until the price drops below A, and we continue. So, to be precise, let's fix the stopping times that are involved with this strategy. Tau naught is the smallest time that the price drops below A. Tau 1 is the smallest time bigger than tau naught, where the price rises above B. Then tau 2 will be the smallest time bigger than tau 1, when the price again drops below A. Tau 3 will be the smallest time later than tau 2, for which the price rises above B, and so on. Here's a graphical representation. Here is one sample path of our submartingale, and we've set A equal to 4 and B equal to 6 in this example. So we see tau naught in this example is at time 0 because it starts out with a price less than or equal to A. And then tau 1 is here when we reach the height 6. Then it drops back down and it hits price A, so that's tau 2. It goes up but it doesn't stay up, so it wiggles around, and then it hits price B again, so that's time tau 3. We sell there, and afterward it doesn't matter what happens for a while. It goes up, then comes down, down, and it hits price A again, so we buy again. There's time tau 4. And it goes up, but not enough. So we hold on to our stock here, bite our nails as it drops below A and stays down for a while, but eventually comes back up to B, and there's time 5 when we sell again. And all of this will be disappointed that we sold because it's staying above B, but anyway, we're employing our strategy and we don't buy again until we get here, and so on down the line. Of course, all of these are stopping times for our process. Our process is adapted. Tau 0 is the hitting time of the interval from A downward. Tau 1 is the hitting time of the interval from B upward after time tau naught. And as we've shown, if you have a stopping time, then a hitting time after that stopping time is also a stopping time. So therefore, continuing by induction, we see that all of these are in fact stopping times. Okay, so the betting strategy, buy low, sell high, can be described in terms of those stopping times as follows. We're taking AN to be the sum, k going from 0 up to infinity, of the indicator that n is greater than tau 2k, the even taus are the ones where the price drops below a, and that n is less than or equal to tau 2k plus 1. The odd indexed stopping times are the ones where the price rises above b. Now remember, we've set up our stochastic integrals so that we're buying an amount at every time step, but we can use that to model buying and holding on to our stock by just buying and selling that same amount repeatedly during the interval on which we want to hold on to it. And so that's why this exactly models the buy low, sell high strategy, because what we're saying is we buy one amount of stock at each turn after the price falls below A, but before the next time it rises above B. And then once it rises to B or higher, we stop buying until the next term in this sum. So that exactly describes the buy low, sell high strategy. And if we want to be precise, we better make sure that it actually is a valid strategy. That is, it has to be non-negative. Okay, it is, as we can see. It's a sum of indicator functions that are all disjoint from each other, so it takes values 0 or 1 at any time step. And we need to see that it's predictable. Okay, well, this is the same thing as the indicator of the event that tau 2k is less than n times the indicator of the event that tau 2k plus 1 is greater than or equal to n. And so to check that this is predictable, we just need to check that these two events are in fn minus 1. Well, the event that tau 2k is less than n is the same as the event that tau 2k is less than or equal to n minus 1. And because tau 2k is a stopping time, that means that that's in fn minus 1 as needed. Whereas the event that tau 2k plus 1 is greater than or equal to n is the complement of the event that tau 2k is less than n. And for the same reason, that's in fn minus 1. Therefore, the original event is also in fn minus 1. And so that shows us that an is a predictable process. So this is a valid betting strategy. Now that means that it does not do any better than the all-in strategy, as we've proved. But we'd like to understand how well it does do. Well, to understand that, we look back at the picture here and say, look, what we know happens and what was designed to happen is every time we cross from A up to B, we make a profit of B minus A. Now then we have to wait a while until we drop back down to A and then cross back up to B. But when that happens again, here's another upcrossing. And now we make another profit of B minus A. And continue here. Oh, now there's a whole period here where we're down, but eventually we do get back up to B. So from here to here, there's another upcrossing. And during that interval, we make another profit of B minus A. So what counts here are the number of times we cross up from A to B. Let's make that precise. For each time n, unx of A and B is the number of times that the process x crosses A up to B upward. We can make that very precise in terms of the stopping times. This is exactly equal to the smallest integer k, such that the odd-numbered stopping time tau 2k minus 1 is less than or equal to n. Those odd indexed stopping times are the times that we reach B after having started below A, and we're asking for how many times that happens during the interval from 0 up to n. And that's exactly the number of odd numbers between 0 and 2k minus 1, which is k. So let's look back at our example here. We have one upcrossing, then another one, 2. The next upcrossing is here, 3. And all of this is not, but we have 4. And down for a while. And 5. and up for a while, and then down. Oh, and okay, we had 5 upcrossings here. And so that means we should expect our profit to be about 5 times 6 minus 4. Except that we paid a penalty because our last purchase here, when the price dropped down to A, never got recouped. By time 100, when we stopped, we never got back up to B, and so we just lost that amount of stock. So there's a penalty over there for not completing the last upcrossing. On the other hand, there was a bonus because at the beginning we started well below A down here, and so we have this extra profit. So let's make that precise. If we want to keep track of the exact amount of profit that we make using the buy low, sell high strategy, well, our intuition is that our total profit up to time n should be about B minus A times the number of upcrossings in the interval from 0 up to n, but it could be more than that if the price started below A, like in our example, but it could also be incremented a little less than that if the price stays below A around the end time n of when we're betting. Now we can make that exactly precise and say that we can lower bound our profit, Wn. It will be lower bounded by B minus A times the number of upcrossings, with a bonus for that amount that we had at the beginning, that is A minus x naught, if at time x naught the price is less than A, but also we have our penalty of A minus xn, the amount at the end that we lose if the time at the end is less than or equal to A. Now that will actually be exact if we're talking about a model like this one, where we actually have steps of only size 1 each time, which means that for the price to fall below A, it has to actually hit A on the way. And similarly, for the price to rise above B, it has to hit B on the way. So in that case, that lower bound will be exact. More generally, we don't need to have steps only of size 1 here. It could be that the first time that the price drops below A, it actually drops down to 0. And then we'd get an extra bonus, and so forth. So in general, this is only a lower bound. But that's all we really need for what we're going to use it for. Now let's write this in a slightly different way that's going to be useful for us. So that first term we'll leave as it is. The number of upcrossings times the difference, B minus A. And then this is exactly equal to the negative part of x naught minus A. Whereas this is equal to the negative part of xn minus A. Remember, the negative part of a function is a non-negative number. So that's about all I want to say right now about using this particular betting strategy in order to make a profit. But now I'm going to turn this on its head and use this bound in order to say something extremely powerful about how many upcrossings we should expect our submartingale to have. And that is Doob's upcrossing inequality, which says the following. If xn is any submartingale, if we have 2 bounds a less than b, which are finite numbers, then for any finite time step n, the expected number of upcrossings of our submartingale from a up to b in the time interval from 0 up to n is no bigger than 1 over b minus a times this difference, the expected value of the positive part of xn minus a minus the expected value of the positive part of x0 minus a. Now, just looking at that, you might wonder, is that even a non-negative number? Couldn't that be negative? In that case, we'd have a real problem here, since this is a non-negative integer-valued random variable. Well, I just want you to note that, in fact, since xn is a submartingale, so is xn minus a, and then the positive part of that, which is the maximum of xn minus a and 0, well, that's also a submartingale, because the function g of x being the maximum of x minus a and 0 is a convex function that is also increasing. And therefore, that function of the submartingale xn produces a new submartingale, which means that the expected value of that submartingale is non-decreasing, which is exactly to say that this is a non-negative number. So let's prove the Doob upcrossing inequality right now. It actually follows very easily from that estimate we gave for the amount of profit produced using the buy low, sell high strategy. If we let AN denote the buy low, sell high strategy for A and B, as we just went through, and let WN denote our profit beyond our initial fortune up to time N, then from the first result we proved that the all-in strategy is king, we know that the expected value of this increment to our fortune is no bigger than the expected increment in the stock price during that time. But the increment in the stock price can be written as xn minus A minus x naught minus A. And therefore, this is bigger than or equal to our expected profit. But from the inequality that we just proved for our profit involving the upcrossings, that is right here, that tells us that this is greater than or equal to the expected value of B minus A times the number of upcrossings plus x naught minus A negative part minus xn minus A negative part. And now all we have to do is rearrange that to see that B minus A times the expected number of upcrossings is less than or equal to this minus the expected value of all of that. And when we do that subtraction, we have xn minus A minus the negative of xn minus A negative part, so that's the sum of those two, minus x naught minus A minus the negative part of x naught minus A, so that's minus the sum of those two. But the sum of these two is, by definition, the positive part of xn minus A. Indeed, for any function, f is equal to f plus minus f minus. That's what we're using here. And similarly, this is equal to the positive part of x naught minus A. And so we get exactly the inequality that we have written here, concluding the proof. Now that shows us a few things that are intuitively clear. For example, if we take A and B farther apart, the expected number of upcrossings must go down, of course. But aside from some applications to our thoughts about choosing A and B in our buy low, sell high betting strategy, this inequality is actually an extremely powerful tool for understanding the properties of submartingales. In particular, this number of upcrossings is related to how oscillatory our paths of this process are. And so this inequality tells us that the number of up oscillations in a time interval is controlled in a uniform way by something to do with the difference in the values at the beginning and the end in expectation. So in particular, if there's some kind of uniform control on the right-hand side here, which will be provided if our submartingale is L1 bounded, then our process can't really oscillate very much. As we'll see next time, that's going to imply that L1 bounded submartingales actually converge as n goes to infinity.